Yeah, good evening to all.
Good evening, sir.
Good evening, sir.
Now I am introducing Sir ఉన్నారు ఇక్కడ ఒకసారి సార్ బ్రీఫ్ ప్రొఫైల్ చూసిన తర్వాత మనం I'm very happy to introduce Dr. B. Pradeep. His native is Suryapeta. He completed his schooling at Suryapeta district. He completed his graduation from SV College, Suryapeta. He completed his MSc from IIT Madras, and he joined as a PhD Indian Institute of IISc Bangalore. Under the guidance of Professor S. Tangavelu, he completed his PhD in 2015. His research area is complex analysis, that is harmonic analysis. He published many research papers, various SCA and Scopus Index journals. Presently, he is working as assistant professor BITS Filani from 2015 onwards. And also, he has very much knowledge in pure mathematics. Now, I request Dr. B. Pradeep sir for accepting my invitation to deliver guest lecture. I once again thank to Pradeep Kumar sir accepting my invitation. On behalf of Fermat Educational Academy, I'm saying a special thanks to Dr. Pradeep Kumar. Please sir, please start your lecture on linear algebra. Sir, please start, sir.
Okay.
Welcome to Pradeep Kumar sir.
Okay. Thank you, Nagesh sir, for giving elaborated introduction about me. I'm very happy to deliver a lecture in your institute. So I'll start first lecture on linear algebra. Am I audible clearly?
Yes, sir. Yes, sir. You are clear, sir.
Okay. So, yeah, before I start, if you have any doubt at any step, you can ask me. You can unmute and ask the doubts. You can stop anytime. And if you don't understand my writing or my words, you can always ask me. Okay.
Yes, yes,
Before starting linear algebra, I just want to give what is how linear algebra play role in the solving of system of linear equation. Okay, manam system of equations ante telusu kada, linear system of equations, everybody know, right? Yeah. So system of linear equation means we have some collection of linear equations that we call system of linear equation. So linear equation means this is, you see, for example, this equation. So we have unknown x1, x2, x3. These are unknowns. And a11, a12, a13, and b1 are knowns. So if you have unknowns, and if it is the equation in linear equation in unknowns, then we call it as linear equation. Linear equation means if you have x, for example, I will give one example. 2x plus 3y plus 2z equal to, suppose 3. So it is a linear equation in x, y, z. Okay, that means it is like a polynomial, but the first degree polynomial. First degree polynomial in x, y, z we call linear equation. So this is the standard definition of linear equation. Then we have a system of linear equation. I'm considering only 3 linear equation in 3 unknowns. I have written here. Can you see this? And here b1, b2, b3 are scalars coming from real numbers, and a11 and a12, so on, a33. These are also scalars, and x1, x2, x3 are unknowns. This we are calling variable. So we want to find x1, x2, x3 satisfying these 3 equations. That means the system of this system of linear equation. So one has to solve this equation. These equations we can write in the matrix form. I think everybody know, right? We can write in matrix form. Na, you take the coefficients. One coefficients తీసుకొని a is equal to a11, a12, a13, then a21, a22, a23, a31, a32, a33. These are the coefficients of x1, x2, x3 in these 3 equations, right? So this is A, and then we can write this system of equation as Ax is equal to B, where B is, I have written here, B is B1, B2, B3. Okay. It's a vector. Okay. Okay. So now we want to solve this this system of equation. Indirectly, we want to find x, vector x. I will tell you why we are calling vector x. Here vector x satisfying Ax is equal to B. B is known, A is known. So how do you solve this equation? So how do you know that there is a solution? When do you say that Ax is equal to B has a solution? ఎవరైనా చెప్పగలుగుతారా Ax is equal to B ఎప్పుడు ఉంటుంది solution?
Determinant of A not equals to zero.
Yes. So if you know rank of A, B, augmented matrix. This is called augmented matrix. If rank of augmented matrix is equal to rank of A, we say that it will have a at least one solution. Then system 1 has at least one solution. Right? This everybody know. But what is the proof of this one? Can someone tell me the proof? Okay, I don't want to ask you because it may be easy, it may be little tricky. I want to prove this thing before that. So how do you prove? So you write Ax is equal to, sorry. కొంచెం హ్యాండ్ రైటింగ్ అర్థం కాకపోవచ్చు, అర్థం కాకపోతే అడగండి ఎక్కడైనా.
Yeah, clear sir, clear sir.
Okay, Ax is equal to B is same as A11, A12, A13, A21, A22, A23, and B3, A31, A32, A33, X1, X2, X3 equal to B1, B2, B3. So this is this equation we are writing like this. This is if and only if. Can you see this one? X1 into vector A11. This matrix multiplication I am writing in a different way. A21, A31. ఇంకో రకంగా రాస్తున్నాను ఈ matrix multiplication. X2 into A12, A22, A32 plus X3 into A13, A23, A33, which is equal to B1, B2, B3, right? Can I write this matrix multiplication like this? Okay. So this is same as, that means, so here I'm assuming some terminology from linear algebra. లీనియర్ ఆల్జీబ్రా మీకు తెలుసు అనుకుంటున్నాను, సమ్ టర్మినాలజీ మీకు తెలియకపోయినా కొద్దిసేపు మీరు అజ్యూమ్ చేసుకోండి. ఆ తర్వాతకి మళ్ళీ ఇందులో యూజ్ చేసిన ప్రతి ఎవ్రీ టర్మినాలజీ ఐ విల్ బి ఎక్స్ప్లెయినింగ్ ఇన్ ద కోర్స్. ఓకే, సో ఇట్ ఈస్ నథింగ్ బట్ B1, B2, B3 belongs to span of A11, A21, A31, right? ఇక్కడ B1, B2, B3 is the linear combination of this this vector, this vector, this vector. So that's what I'm writing. B1, B2, B3 belongs to span of A11, A21, A31, and A12, A22, A32, comma A13, A23, A33. Can you say that this? So B1, B2, B3 span lo unnanna. There exists X1, X2, X3 satisfying this equation on the same. Rendu equivalent annattu. So this is nothing but, so here we are using non-trivial thing. Dimension of span of, I will tell you all the terminology later. A21, A31 is A21, A22, A32, A13, A23, A33, and B1, B2, B3. Span means set of all linear combinations of finite members of this set. Set of all linear combination of vectors of this set, we call span of this set. So I will be giving all the definition during the course, very nice way. But time being, you assume this one. So here I'm using this results. Dimension of this is equal to dimension of A11, A21, A31, dimension of span of, sorry, here span is missing. And A21, A22, A32, and A13, A23, A33. Okay, so if B1, B2, B3 is there in the span, that means dimension of span of this is equal to dimension of span of this one. I think I have written A11, A21, 31. It's correct, no?
Yes.
Yeah, and this is A12. Is there any mistake in this? Because here I am writing x1 into this vector, x2 into this vector, x3 into this vector. That means B1, B2, B3 is in the span of this vector A12, sorry. This is 1, 2. So similarly, this is 1, 2. This is 1, 2. Okay, so if B1, B2, B3 is in the span, if you add that vector in the set, the span of that set will not change. So we will have a same space by adding B1, B2, B3 in the set. And if you take the span and without adding that B1, B2, B3 in the set, you will get the same vector space. So that's why the dimension is same. So what do you mean by dimension of this? Dimension of vectors is nothing but rank of matrix. In that you have to write the vectors as columns. That is another thing. Another thing I'm using. Dimension of vectors, dimension of span of this thing. I'm sorry, I'll write. Dimension of span of, suppose V1, V2, so on Vk, and V1, V2, so on Vk are in Rn. So vector. So this is nothing but rank of, you write a matrix V1 as a column, V1 as a column, V2 as a column, V3 as a column, so on Vk. So this concept I'm using. So this also we will see. This we will prove later. Okay, by using this idea, we can write the by using this concept, we can write dimension of A comma. If I write this vectors as columns, you will get A matrix. You will get back A, right? Then we write the B vector. So this is augmented matrix. So dimension of A. So this is what we will see. So that means there exists x1, x2, x3 satisfying the system of equation if and only if B1, B2, B3 is a linear combination of columns of matrix A. That means B1, B2, B3 is in the span of columns of matrix A. These are columns, right? Sorry, these are columns. And then this is same as, so if it is in the span, then the dimension of in the span is same as dimension of the span set. You add that extra vector, span vector V. If you add in the set, we will get this. So that is how we will get this result. Okay, you understand now? So that's why to understand the solution set of a system of linear equation, for the existence of solution for the system of linear equation, we need to study linear algebra. So that way it is useful. Okay, so we will start with linear algebra. And linear algebra has so many applications, but here this is not the class to give application. Here we are interested to solve the different problems in linear algebra. Okay, before I define vector space, so we need to know linear algebra. So we need to know first groups. Okay, we need to know what is a group, and then we need to know what is a field, and then we will define vector space. Okay. We need to know group, field, vector space. Okay, first I will define a group. So do you know what is a group?
Yes, sir.
So group means group is a non-empty set. So I will give the definition. A non-empty
User
set.
associative identity units.
Yes, a non-empty set G is said to be non-empty set. Sorry, G is said to be group if is said to be group with respect to a binary operation. Sorry. With respect to a binary operation dot if, so this binary operation we call product. First property into the first we call G1 property. If A, B belongs to Z, then
Closure property.
A dot B belongs to G. Yeah, this is called closure property. Called closure property. And then if you take G2, another G2 is A comma B,
C.
C, both A, B, C belongs to Z, implies A dot B bracket B dot C equal to A dot B dot C. So this should be satisfied. That means you multiply first B and C, then multiply A, and same as you multiply A and B and multiply C.
Associative property.
This is called associative property. And G3, another property G3 we are calling. G3 is there exists an element E belongs to G. There exists an element E belongs to G such that A dot E is equal to E dot A equal to A. That means if I multiply A with this special element E and E with A, you should get A. What do you call E here?
Identity element.
Identity element.
Yes. Identity element. So this is especially is called identity with respect
Element.
to the particular operation. And G4 for every A, what is G4? Can you someone tell me?
Inverse property.
Inverse
Did you say
property.
A inverse?
A
Inverse
into
property means for every A and for every A in G, there should exist A inverse.
A inverse is
A
also
inverse.
found such that A into A inverse equals to A inverse into A
Inverse into A
equals to
equal to E.
Oh, so everybody, I mean, so you didn't forget this definition. Good. A into A inverse. So here, can I know what are the audience like? Are these people are doing fresh MSc are preparing only this JL or SC?
Sir, here fresh MSc and old 2002 completed their MSc. There is a gap between around 20 years. Students are there. Then
Okay.
continuous teachers is there. JLs and DLs and university teachers also there, sir. Some contractual teachers.
Okay, good.
ఆల్ కేటగిరీస్ ఉన్నారు సార్, అందరు ఉన్నారు. కాబట్టి మనం బేసిక్ లెవెల్ చెప్పుకుంటే బెటర్ అనేది.
అవునవును, అదే చూస్తున్నాను. So now here E is called identity and A inverse. For A belongs to G, A inverse is called inverse of A, right? Now we'll see example. Consider the set of integers. So generally the set of integer is denoted by capital Z. I think you know, with a double line. Okay, and if you take with usual addition, we can verify that if 1 for m comma n belongs to Z, we know that if you take the sum of two integer, it is another integer, and this usual addition is associative. That means m plus n, m plus of n plus l, yeah, which is equal to m plus of n plus l for all m comma n in Z. And we know that the Z has 0 element. So we know that 0 belongs to Z satisfies 0 belongs to Z satisfies L plus 0 is equal 0 plus L is equal to for all L. So that means there is identity. And what is the inverse of suppose fourth property? If I take M belongs to Z, what is the additive inverse of M? Minus M. So minus M plus N. If M is there in integer, minus M is also an integer. So there exists minus M in Z such that M plus minus M equal to minus M plus M equal to this. So that's why we can say that Z comma Z is a group with respect to addition, with respect to usual addition. So when here I am using some notation, you see Z comma plus. So that means group is a order pair. Group is a order pair with one is non-empty set. Group is an order pair. Which consists of non-empty set, G, and a binary operation. So which is denoted by G comma dot. It is denoted by G comma dot. Okay, now we will see another example. Example 2. Let x is equal to x1, x2, x3. Capital X is equal to small x1, x2, x3. And S3 be the set of all bisection maps. And S3 be the set of all bisection maps on X. Bisection maps on X. Capital X. On capital X. So can you guess an operation on S3? Can you give an operation on S3? Binary operation. Binary operation means మీరు రెండు ఎలిమెంట్స్ తీసుకోవాలి. ఆ రెండు ఎలిమెంట్స్ మధ్య బైనరీ ఆపరేషన్ ఆపరేట్ చేస్తే మళ్ళీ ఆ ఎలిమెంట్ రావాలి, అందులోనే ఎలిమెంట్ రావాలి.
Composition, sir.
Composition, right. So here we take F comma G belongs to S3. F composition G is defined. F comma G belongs to, for F comma G belongs to S3. F comma G of X. F composition G from X to X. Map X to X. X to X defined by F composition G of X equal to F of G of X. So now tell me, is it a closed? Is this operation closed? ఈ ఆపరేషన్ క్లోజ్ అవుతుందా? రెండు బైజెక్షన్ మ్యాప్ కంపోజిషన్ చేస్తే మనకి ఇంకో బైజెక్షన్ మ్యాప్ వస్తుందా రాదా? If you composite two bisection operator, what do you mean by bisection map? Bisection map అంటే ఏంటిదండి?
Close it.
1 1 and on 2.
1 1 and 2.
A map on a set A is said to be bisection if it is 1 1 and on 2. 1 1 and 2 means 1 1 means different elements should be mapped to different elements. On 2 means in the codomain every element should be mapped. Range of map equal to codomains. I think these are, I am assuming that you know all these things. So this also you know. Composition of two bisection map is again a bisection map. So that's why this composition is closed on S3 first. So F composition for every F comma G belongs to S3. F composition G is also in S3. So and we know that composition is associative. This you have studied in 12th standard when function theory, right? F composition of G composition H equal to F composition of G composition H for all FGH belongs to S3. And what is the identity element here? Third one. Identity element,
Identity operator.
identity operator, identity function. Fi, F composition I equal to F, where I is F, where I is, how do you define I of X is equal to X? For all X belongs to capital X. That means I of X1 is equal to X1, I of X2 is equal to X2, I of X3 is equal to X. And also I composition F is also F1. I composition F is also, I composition F is also F. So that means F composition I composition F equal to F means this identity operator is unity, it's an identity element with respect to composition. So there is a, this is a, identity operator is also bisection operator, right? The, I belongs to S3. Therefore, we know that I belongs to, here I belongs to S3. So that means S3 has identity element. And fourth property. So do you have an inverse of inverse with respect to this composition? Suppose F composition G is equal to identity. How G is defined? So G of Y is equal to X. When do you say G of Y is or G of X is equal to Y? We say G of X is equal to Y.
Onto.
No. What is the G? G here. How do you define G? If you know F.
Bisective function.
F inverse.
G of X
F
equal to
inverse.
minus
G is equal to F inverse. How it is defined? How it is defined?
G of Y equal to X.
Yes, G of Y is equal to X. If F of X is equal to Y. ఒకవేళ F అనే ఫంక్షన్ X ని Y తో మ్యాప్ చేస్తే G అనేది ఏం చేస్తుంది Y ని X తో మ్యాప్ చేస్తుంది. అదే కదా ఇన్వర్స్ అంటే. సో ఇన్వర్స్ అంటే F అనేది X ని Y కి మ్యాప్ చేస్తే ఇన్వర్స్ ఆఫ్ F అనేది X ని Y ని X కి మ్యాప్ చేస్తుంది. సో రివర్స్ చేస్తుంది. సో అది అట్లా డిఫైన్ చేస్తాం. సో ఇఫ్ F belongs to S3, can we say that G belongs to S3? That means if F is bisection, can you say that G is also bisection?
Yes.
Yes.
Sir.
First of all, I forgot to tell you, every time G may not be well defined. Here F is in S3. F అనేది S3 లో ఉందంటే F అనేది S3 లో ఉందంటే 1 onto 1 onto అయితే దానికి ఇన్వర్స్ ఎగ్జిస్ట్ అవుతుంది. We know that. We have seen in 12th standard. That's why G also 1 onto. So we know that if F is in S3, there exists G such that F composition G is equal to identity. So then F inverse belongs to S3, which is G. Okay. Now this we can see. Can you say this thing F composition G is equal to G composition F for every? Can we say that F composition G is equal to G composition F for all F belongs to S3? F comma G belongs to S3. నేను F ని G ని కంపోజిషన్ ఏ ఆర్డర్ లో చేసినా ఒకటే వస్తుందా మనకు? ఒకవేళ ఇలా అయితే ఏమంటారు S3 ఏమవుతుంది అది? But it is not true. Do you have any example? Composition of matrix. ఈ ప్రాపర్టీని ఏమంటారు? AB is equal to BA or F composition G is equal to G composition F. Do you commutative property?
Two properties.
Yes, I'm indirectly asking, is S3 commutative? Now S3
No, sir.
No, sir.
No, sir, not.
I forgot to say, yeah, S3 is already group with respect to composition. Here, therefore, S3 is group with respect to composition of maps. Now I'm asking FG is equal to GF for every F comma G belongs to S3. So that is not true. One example you can give easily. For example, F is X
Sir,
squared.
it is not a abelian group.
Yes, it is not abelian. Commutative or not abelian means commutative is same as abelian. So f is from x to y. We are defining f is from x to y defined by f of x1 is equal to x2. I'm just giving one example. X1 is equal to x2. F of x2 is equal to x1. F of x3 is equal to x3. And g, another element, g is from x to x. I'm sorry, here I should write x to x. G is also from x to x. X, you remember, x is x1, x2, x3. Defined by g of x1 is equal to x2. G of x2 is equal to x3. G of x3 is equal to x1. Now, if you now what is F composition G? F composition G. F composition G. X1 goes to x1. If you take x1, what is the image of x1 under F composition G?
X1, sir.
X1 goes to x1. Yes, you can just easily see x1 goes to x1. X1 goes to x1. I'm sorry, I forget. X1 goes to x1.
X3.
F is, we will write directly or we will, okay. So this is F. And then this is F. And this G, what is G is here x1 goes to, yeah. F is this one, right? First map is F, second map is G. Now now we are finding G composition F. One minute. So what is F composition of x1? F composition G of x1? Somebody told. What is that? F of G of x1. X1 going to G of x1 is x2. And F of x2 is x1. F composition G we are finding. So F composition G of x1 equal to F composition G of x1 equal to x. So which is F of x1? F of G of x1, which is equal to G of x1 is x2, and G of F of x2 is x1. So we can directly write. I have calculated. This is elementary calculation. F composition G will be, similarly you can calculate. X1 goes to x1, x2 goes to x3, x3 goes to x2. And G composition F also we can calculate. X1 goes to x3, x2 goes to x2, x3 goes to x1. Is this clear? Now you see these two functions are not equal. Why? Why these two are not equal? When do you say two functions are equal?
Domains, codomains must be equal, and f of x equal to g of x.
Yeah, domain should be equal, codomain should be equal, and f of x is equal to g of x for every x. Here codomain, domains are same, x only, but only thing is that you see x1 is mapping to x1, here x1 is mapping to x3. So f composition g x1 is not equal to g composition of f x1. So both are not same, right? So yes, but whereas in Z comma plus, this is a group, we have that m plus n is equal to n plus m. Okay, so in a group we may not have always AB is equal to BA. Sometimes it may be true for all A comma B, sometimes it may not be true. So those groups which satisfy this property, AB is equal to BA for all A comma B belongs to G, we call it abelian group. Yes. Abelian group we will define soon. Is a abelian group. Is an abelian group. So we can define now what is abelian group. Abelian group definition, a group so G comma dot is a group is said to be abelian. A group is said to be abelian if AB is equal to BA for all A comma B belongs to G. So examples you can give me plenty of examples. We already saw Z comma plus. Z comma plus is an abelian group, and S3 comma 0 is not an abelian group. You can write S3 comma composition, not plus. Z comma plus is abelian group, and S3 comma composition. Is non-abelian, not an abelian group. Okay, we are more interested this group Rn. You know what is Rn? Rn equal to
N tuples are
n tuples of real numbers. That means set of all x1, x2, so on xn. Each such that each xj belongs to R. This is n tuple of R. So and now I'm defining an operation here. For x belongs to R, x comma y belongs to x is for x is equal to x1 so on xn. X is equal to x1 comma so on xn tuple, and y is equal to y1 y2 so on yn. Both are in Rn. Then I'm defining addition in Rn. So we are defining operation x plus y. We call its usual addition. Standard addition in Rn is x plus y, which is defined by x1 plus y1, x2 plus y2, so on xn plus yn. So we know that this is a group, right? This is a operation, binary operation. Because if you take two n tuples, if I add n tuples, you are getting another n tuple. X plus y belongs to Rn. So it's a binary operation. So can you verify it's a group Rn comma plus? Is it a group?
Yes,
Which
it is a group.
And is it abelian?
Yes, it is abelian.
Yes, it is abelian. So it's a group and abelian. So do you have? So what is the zero element in this?
0, 0,
0,
so on.
0, 0, n tuple 0. N tuple 0.
Equal to O or 0 equal to 0 comma 0 comma 0. And what is the inverse of x minus x equal to? What is
minus
inverse?
x1 minus x2 up to so on minus xn.
Yes.
So on minus xn.
Yes. So it is a group with respect to this plus. This plus we call usual addition and Rn. Okay, we will come back to this group later. And if you take a space of all matrices, another example, matrices of over real numbers, m by n of R. I think this everybody know this notation. Do I need to define this notation? Set of all A equal to Aij, where Aij belongs to real number. It's a m by n matrix. And it is what is a matrix addition? Usual addition and matrices A plus B equal to A comma B belongs to m by n of R. A comma B belongs to m by n of R. So A plus B, how it is defined? You have to add component wise addition. So you take A11, yeah, which is equal to Aij plus Bij. Addition is equal to Aij plus Bij. You have to add corresponding terms. So this is the usual addition. We know that m by n of R is also a group with respect to this operation. M by NR comma plus is a abelian group, right? Now we'll take another example. So similarly, we can prove before going to another example, M by N of C. M by N of C. M by N of C. With respect same operation. This is also an abelian group. We can prove. Now another question for you. This also you check. Set of now you take G, capital G, Ln, G Ln of R. Do you know this notation? What is this? Student, what is this? Set of all invertible matrices. Set of all invertible square matrix of order n. Invertible square matrix. Invertible. I'm sorry, I'm calling student. You are not student. I usually in the lecture I call a student when I'm doing online lectures. So sorry for that. Set of all invertible matrices of order n by n. So is it a group? Sorry, what is operation? What operation we can give here so that it is a group? Matrix multiplication, right? Somebody has doubt. 1 minute. Yeah, no doubt. Okay, so can you give an operation on this so that it is a group? Can you hear me? So operation is in matrix multiplication. This dot is here matrix multiplication. It's a group, right? Okay, you can check this one. Anyway, we are not much interested to see more about groups. I think another faculty will be teaching about the group theory. So, but same group is I'm taking the same set GLN of R, and with respect to addition, is it a group? Is it a group? Excuse me, is it a group? Yeah. If you add two invertible matrices, do you get another invertible matrices?
Actually, sir, group theory college, sir.
What are these? Okay. So after this group, we need a field. So before field, shall I define ring or directly shall I define a field? Maybe I'll define directly field. Okay. Field. So a non-empty set with two of a non-empty set F is said to be field. With respect to two operations, with respect to
Two operations.
plus and dot, yes. Plus is called vector addition. Sorry, addition we call not vector addition. Sorry, it's a simple addition, and dot is called multiplication. When do you say it's F comma plus if F comma plus is an abelian group.
With respect to addition.
Yes, with respect to addition. And F comma dot.
Dot also abelian.
0.
Abelian with respect to multiple.
F minus 0. F minus 0. F minus 0. Here, what is 0? 0 means additive identity. F minus 0. should be an abelian group. An abelian group. Here 0 is additive identity. Additive means here addition we have no additive identity with respect to identity with respect to that addition. Is that enough or are we missing something? So there is something we should also have compatibility distribution laws between these two. So A, B, C belongs to and A, B, C belongs to F. A dot B plus C equal to AB plus AC. And check anyway commutative. So any another property? Yeah, yeah, that's all. So since it is it is a commutative, so this is also implies B dot C, which is also implies B dot C into A. B dot B plus C into A dot A equal to B dot A plus C dot A, because it's commutative group now. So we have this property. So first one is enough. This one is enough. Automatically second one follows. So if you have a set, non-empty set satisfying these three property, 1, 2, and 3. So we call it is a field. So examples, can you give me one example? Anybody know? So examples are real numbers, set of all real numbers with respect to usual addition, usual multiplication. It's a field, right? And Q, set of all rational numbers, Q comma plus dot. It is also field. So why R comma plus comma dot is a field? Because R with we already seen R plus R comma plus is a abelian group that we already know. And if you take dot multiplication, so every non-zero element in R has an inverse, and 1 is the identity. R minus 0. R minus 0 we write R star. And we abelian group. Sorry. And then we already know that B plus C dot A is equal to BA plus CA. This this property also we know this in the real numbers. That's why it is a group. Similarly, Q comma plus comma dot is also it's a field. Q comma plus comma dot is also field. And C comma plus comma dot. C is a set of all complex numbers. It is also field. And we also have F comma. Another one is, do you know any other field other than these three? ZP, there is something called ZP. Z subscript P with respect to addition, modulo addition P plus P and dot P. This is also a field if P is a prime. P is a prime number. Do you know about ZP? ZP you will see in the group. Okay, I think you will. We don't need much about ZP, but in CSR somewhere they may ask about the field ZP. But in JL, I don't know whether they ask in this one. So we will see if it is required. I will define when I will do the problems related to ZP. I will explain about ZP. So these are the standard fields we need. One is real. First one R comma plus dot is the field of real numbers. Q comma plus comma dot is field of rational numbers. C comma plus comma dot is called field of complex numbers. These three fields we need. Once we have a field, then we are ready to define a vector space. So vector space . So now we will fix a field. Let F be a field. We will fix a field throughout the course, be a field. So Field means it's all the properties which are above satisfied. And you have to remember, zero is a zero F or zero is a zero element in F. Identity, zero element means additive identity in F. And one means one is multiplicative identity. We know that field means there are two operations. One is addition and multiplication, right? Zero is the identity with respect to addition. One is the identity with respect to multiplication. This we will be using these notations. So now we'll start. We'll give the definition of vector space. Yeah. Okay. A vector space V. A vector space V over the field we say that we have a one set non-empty set V and over the field capital F. So we are going to define a vector space over F. What is this? It consists of vector space over the field F consists of the following. What do you mean by that? So vector space over a field means there are two things. One is non-empty set V. One, a non-empty set V. What do you call a non-empty set V of objects? The objects in this we called as vectors. Yeah, and there will be two operations. Second one operation on V called vector addition. One operation on V called as vector addition. Another operation, operation plus. This operation we denote with plus. Plus is an operation from V cross V to V. And another operation dot. Called as scalar multiplication. This operation is not an operation on V. It is an operation from F cross V. It is a map from F cross V to V. So that means you take one scalar, scalar means elements of field we are calling scalar. One scalar and one vector elements of V. If you operate, you will get another vector. Satisfying this plus and dot should satisfy the following. U plus V belongs to V. For all U comma V belongs to V. So it's like maybe I will write the first thing satisfying such that V comma plus is an abelian group. I should have written like this first. Say abelian group, that means you know what you mean by that. If U comma V is there, U plus V should be there. And it should be associative. U of V plus W is equal to U plus V plus W. And there exists a unique vector 0V. Unique vector 0V in V such that 0V plus V equal to V plus 0V equal to V for all V belongs to V. So here 0V we call a zero vector. Okay. Zero means it is a zero element in field scalar, but 0V is a zero vector. And another property is that for every V in V, there should exist additive inverse. That means negative V. For every V in V, there exists unique vector minus v in v such that v plus of minus v is equal to minus v plus of v equal to 0 vector 0 v. And I said it is a commutative, that means u plus v is equal to v plus u. So addition, with respect to addition, we should be abelian group. And there is scalar multiplication also. Scalar multiplication should satisfy this following property. If alpha dot v should be, for every alpha dot v belongs to v, for every alpha belongs to f, v belongs to v. And alpha times u plus v is equal to alpha u alpha v. And alpha plus beta, this kind of distribution law. So scalar multiplication over vector addition is distributed, that kind of thing, right? Alpha plus alpha times u plus v is equal to alpha u alpha v. Another way also we should have alpha plus beta times u, that means scalar multiplication dot is equal to alpha dot u plus beta dot u. Another one is alpha times, next another one is alpha times alpha dot beta dot u equal to alpha beta dot . So here see alpha dot beta dot u, here this dot is a scalar multiplication, and here alpha beta we have now alpha beta from where? Alpha beta from f. Here I forgot to write here. Alpha beta belongs to f. So what do you mean by alpha beta? This is a multiplication in the field, and u is a vector. U belongs to v. So alpha beta, it's a multiplication in the field, and this dot product is a scalar multiplication. So this condition should be satisfied. Okay. So, and another last property, 10th property. 1 into v, 1 dot v. One means, you know, na, one means it's a unit vector, unity in the field, identity element in the field. 1 into v is equal to v into 1 equal to, sorry, v dot 1 won't be there. Scalar multiplication is v is a vector. 1 into v equal to v. For all v belongs to v, and 1 is anyway, 1 is identity element. Okay, now we will see example. Here I forgot to tell you what you call elements of V, vectors, and elements of field F we call scalars. You have to remember this terminology. Elements of V are called vectors, elements of F are called scalars. So now very basic and fundamental example is Fn. Example, we will say example. Fn. F superscript n, F superscript n with this is n. So what is this? This is defined by F is any field. So Fn is defined by, it's n tuples of fields, field elements, n tuples of n tuple space, maybe we call n tuple space. This is defined by Fn equal to, like Rn. If F is equal to R, Fn is Rn. How do you define Fn is equal to x1, x2, so on xn? Where x1, x2, so on xn belongs to F. X belongs to, now we are going to define addition and scalar multiplication. X belongs to Fn, Y belongs to Fn, X belongs to Fn, Y belongs to Fn. So X will be of the form x equal to x1, so on xn. Y is of the form y is equal to y1, y2, so on yn. Then we are proposing vector addition. The vector addition is x plus y. Vector addition. We will write first vector addition. vector addition is proposed by x1 x plus y is equal to x1 plus y1 x2 plus y2 so on xn plus yn. Then you should ask what is this place x plus x1 plus y1. X1 here I forgot to tell you xi's and yj's are f, right? So what do you mean by x1 plus y1? So this is a addition. This is a addition in the field. X1 y1 belongs to field, right? So these are the addition in field. Okay, this is understood. So it is these are addition in the field f, addition in f. Now scalar multiplication, alpha scalar multiplication. What is the scalar multiplication? Alpha f. Equal to alpha x1, alpha x2, so on alpha xn. ఇక్కడ మీరు అర్థం చేసుకోవాలి ఆల్ఫా x1 ఆల్ఫా x2 ఆల్ఫా xn ఉందంటే ఆల్ఫా హియర్ ఆల్ఫా is f, alpha is in f, xj's are also in f, right? So then in f we have a multiplication f. So this alpha x1 alpha x2 are the scalar multiplication in f1 only. So this is understood. So we can verify that fn is a vector field. We can verify that. Verify that fn is a vector field. So vector space over f. What is the zero vector here? Can someone tell me what is the zero vector?
0, 0, 0, dot,
Zero,
dot.
Comma, 0, so on, n numbers.
And minus x is minus x minus x.
Minus x1 minus x2.
2
So on minus x. Yeah. So it's a very fundamental example. If f is r, then it is rn. If f is c, it is cn. So if you have a field, sorry, now I want to give some terminology, basic terminology. If E is a vector space over R, over field of real numbers over R, then we call it's a real vector space. Then V is called real vector space. If V is a vector space over C, we call complex vector space. So, and another example is space of all matrices, f of m by n of f. F of m by f, m of f, m by n of f, sorry. M space of all matrices over M, that is denoted over F. Yeah, this f of m by n of f. This is a space of all matrices m by n matrices over f, which is defined by equal to set of all matrices m by n matrices, matrix over f. Over f. That means it is a set of all m by n matrices whose entries are coming from field f. So this is also vector space with usual addition and usual multiplication. Is a vector space. What is the usual addition here? Suppose if you take A is equal to Aij, B equal to Baj, what is A plus B? Somebody said. What is the usual addition here? Usual addition and scalar multiplication. A is a matrix. Let A is equal to Aij, capital A equal to Aij, capital B equal to Bij. Both are in this set. Then A plus B. How do you define A plus B? You have to add component wise. Corresponding elements you have to add. A plus B is Aij plus Bij. And what is a scalar this is called usual addition. What is a scalar multiplication? Alpha A equal to alpha Aij. Alpha into Aij. Alpha, I should write alpha inside the bracket. Yeah. So with respect to this addition and scalar multiplication, it is a vector space over F only. So this is a vector space over F. So if you take F is equal to R, it's a real matrices, and if F is equal to C, this space is called complex matrices, space of all complex matrices. Now there is another fundamental example, F of X. It is a set of all polynomials with coefficients from F. With coefficients from F. F of X, how do you denote? And the set theoretically, F of X is equal to F bracket X equal to summation AK X4K. K is running from 0 to N, where AK are field from the field, and N is any zero natural number or 0, 0, 1, 2, 3, so on. We know this. This you will see in ring theory also. This is called polynomial ring, but we are not taking as a ring. We are going to take it as a vector space. So what now I'm going to define a vector addition. What is a vector addition here? Vector addition. P vector addition for P equal to summation AK X4K. K is running from 0 to N. And Q is equal to summation BK X4K. K is running from 0 to N. So if suppose in the first polynomial, if An is not equal to 0, then this is called polynomial of degree. If An is not equal to 0, what do you call this P? It's a polynomial of degree N. Okay. So now we have two polynomials. I'm going to define vector addition of these two polynomials. P plus Q equal to standard way, usual way. How do you add two polynomials? We will add the corresponding coefficients, right? Corresponding powers of X4K coefficients. So AK plus BK into X4K. And scalar multiplication, alpha P. Alpha belongs to F. Alpha belongs to F. For alpha belongs to F. Alpha is from field. Alpha P is equal to summation alpha AK X4K. So you just multiply alpha inside the polynomial. So this is scalar multiplication. I should have written scalar multiplication here. With respect to this vector addition and scalar multiplication, we can verify that it is a vector space. F of X is a vector space with respect to above operation. Is a vector space over F only. With respect to above operations. With respect to above operations. So now in one problem we will see. So we have seen enough examples. Suppose problem 1. I will a different vector space I am going to define. Let V equal to R plus. R plus means interval 0, infinity equal to 0, infinity. And V is a set of all positive number. F is real numbers, field of real numbers. So now we are vector addition. I am defining vector addition. X plus Y. X plus, this is a vector addition symbol I'm using, plus O plus. So this is equal to XY. For all X comma Y belongs to V. V means R plus, V equal to R plus. And scalar multiplication. alpha dot x equal to x4 alpha. Alpha belongs to R, x belongs to V. So now can you check, is it a vector space? Is V vector space over R? Is V vector space over R? Question is V vector space over R with respect to the proposed operations, vector addition and scalar multiplication? Okay, first we will see this addition, vector addition. So we need to check V comma O plus. Is it a abelian group or not? It should be abelian group, right? Is it a abelian group?
Yes, sir.
Yes. Why? Why it is closed, first of all? Why is it closed under this?
Depend on real number.
Huh?
వెక్టర్ అడిషన్ కండిషన్ లోనే ఉంది కదా.
Yes, vector addition condition ఏముంది అంటే x into y. If x is a positive real number, y is a positive real number. If you multiply two positive real number, you will get positive real number or not. So మనం రెండు positive real numbers multiply చేస్తే we will get positive real number. So it is closed. And we know that with respect to addition, with respect to multiplication, multiplication on real numbers is associated. So we can see that. So x plus of y equal, I will write all the properties. So product of two positive real number is again a positive real number. So therefore x plus x, this plus the special plus o plus, we call o plus x, o plus x dot y belongs to V for all x comma y belongs to R. Yes, and it is associative. It is also associative. X plus O plus x O plus y O plus y z equal to xy. This also you can verify because both sides you will get xyz. So it is true. R plus. I'm sorry, V, it belongs to V. R plus. We have to write in V, right? V. Okay, this is V. R plus equal to V. V equal to V, if you write, that is also fine. Okay, then it's a associative law, and what is the additive identity, vector addition identity with respect to vector addition? Can you guess? Otherwise, if you don't guess, it's no, we no need to guess. We'll write xy is x O plus y is equal to x. Then we have to find out y. Y, right? We will write y here. So for all x belongs to V. So what should be y? Okay, so
I
that
think
means
one, sir.
xy is equal to x, which implies
I equal to
y equal to 1. So now we can also verify 1 plus 1 plus y, 1 plus x is also 1 O plus x is also x, 1 and 1 O plus. Other way also we can verify. So that means it's additive inverse is there. And what about the inverse of x? Additive inverse of x. So we have to see x O plus y equal to y 1 for
1
all.
by x.
Yeah, for no, not for all. Sorry, we have to find given x, y we have to find out. So that means xy is equal to
Y equal to 1 by x or x equal to 1 by y.
yes. So that's why. So if x is a positive real number, then 1 by x is also positive real number, right? Which implies y is equal to 1 by x. Which belongs to V. So it's a closed under this addition. And we can also see it's a commutative, x plus y equal to y plus x. Plus means O plus. So it is commutative. After this, what we have to verify? Scalar, we have to come back to scalar multiplication. So what is a scalar multiplication? Alpha dot alpha O dot alpha O dot alpha O dot x is equal to x4 alpha. This is what given, where alpha is field, means alpha from R, x is from V. Okay, so we know that if you raise the power, x is V means positive real number. If you raise the power of positive real number by any real number, you will get a positive real number, right? x4 alpha is always positive real number, whatever alpha. So it belongs to V, positive real number, sorry. Right? If you take, for example, you take 3 power minus 2. What is 3 power minus 2? 3 power minus 2. Alpha is equal to minus 2. 3 power minus 2. 3 power minus 2. So is it a positive real number or not?
Yes, it is positive.
And if you take 3 power 1 by 2, another one example. So 3 power 1 by 2. It is also root 3, positive square root of 3. It is also positive real number. So x4 alpha is always positive real number. So it is closed. Scalar multiplication is closed. Okay, next we have to see other properties. What is other property? We have to see that, can you recall other property? Alpha O times x plus xo plus y equal to, we have to verify this one, x alpha O dot,
Vector addition.
yeah, distribution over vector addition. Yeah, alpha O dot O is x plus y is xy. So alpha O dot xy is equal to xy whole power alpha by definition. So which is equal to x4 alpha, y4 alpha. So x4 alpha plus O plus by definition x4 alpha x bracket O plus plus y power alpha O dot y. Clear, right? So this we can verify. Similarly, other one, what is the eighth property? We have to, eighth property is alpha plus beta. Here you have to be careful here. Here we have to take alpha plus beta in the field. What is the field here? Real numbers. So what is the addition in the real numbers? Usual addition. So alpha plus beta O dot x equal to, by definition, x power alpha plus beta. This we know. It's a scalar multiplication definition. X power alpha, which is equal to x power alpha into x power beta into y x power beta. So by definition, x power product means x power alpha dot x plus O plus and beta dot x. So that means this property is also true. And what is the ninth property? Ninth property is alpha O dot bracket beta O dot x, which is equal to alpha O dot x4 beta, which is equal to x4 beta whole power alpha. What is this, student? Oh, sorry. What is this? It is x4 alpha beta. We know this, which you can write alpha beta O dot x. So this is also true. And what is the 10th one? 10th one, we have to prove that 1 into 1 O dot x equal to x4 1, so which is equal to x. So 1 into x is also x. So all properties are satisfied. So it is a vector space. So another question I will give, you should tell me this one. So now onwards we will see examples only. Not last example, it's exercise. V equal to R2, F is equal to R. And then we are defining x1 y x, now vector addition, v addition, vector addition, x1 comma y1 plus x2 comma y2 equal to usual addition on x1 plus x2 comma y1 plus y2. And then scalar multiplication alpha dot x comma y equal to alpha x comma 0. So scalar multiplication. So verify with respect to this operation, is V vector space over F? Is V vector space over F? Is V vector space, is V vector a vector space over F with respect to above operation? ఈ రెండు ఆపరేషన్స్ ఇచ్చాను, వెక్టర్ అడిషన్ ఇచ్చాను, స్కేలార్ మల్టిప్లికేషన్ ఇచ్చాను. విత్ రెస్పెక్ట్ టు ఈ రెండు ఆపరేషన్ తోని వి వెక్టర్ స్పేస్ అవుతుందా కాదా? కెన్ యు క్విక్లీ టెల్?
Yes, sir. It is vector space.
Why? It satisfies all the properties, right?
Yes, sir.
But you see last property 1 into x should be x, right? 1 into x is x.
X comma 0.
It's not x, na? X comma y. 1 into x comma y should be x comma y. But we are not getting x comma y. We are getting x comma 0.
Yes, sir.
So-
Last condition failed.
So what I'm saying that it looks all the properties are satisfied, but by last property is failed. If one of the properties failed, then it is not a vector space. So you have to be careful. Okay, we have to see all the properties. 1 dot x comma y is not equal to x comma y. It is x comma 0. So it is not it's not equal to x comma y if y is not equal to. If I take y is non-zero, then it both are not zero, both are not same. So it is not a vector space. So there are some more examples I will we will do next class. Okay, I will stop with this. If you have any doubt, you can ask me.
No, sir, you continue, sir. If you want to take 10 minutes, no problem, sir. No issue.
We can continue.
10 or 15 minutes, as your wish. As your wish.
Okay, okay. So I will give one more example. I will ask one more example. So this is not a vector space. Another is we'll take same. V is R2, F is R, and vector addition is usual addition. X1 comma y1 plus x2 comma y2. X1 comma y1 plus x2 comma y2. X1 comma y1 plus x2 comma y2 is equal to x1 plus x2 y1 plus y comma y1 plus y2. No, not I'm sorry, I think this is different operation. X1 plus x2 plus 1 comma y1 plus y2 minus 2. So vector addition. Okay, I'm proposing this as a vector addition, and scalar multiplication is alpha dot x comma y equal to alpha x plus alpha minus 1 alpha y minus 2 alpha plus 2. Question is that is it a vector space with respect to these operations? Is V vector space? And I don't write every time with respect to operations. You have to understand. Is V vector space a vector space over F? Answer, you have to verify this one. Okay, this is an exercise. And another one. This is a you have to verify. You tell me in the next class. I will ask you. Another example. P equal to R. V equal to R. F equal to Q. And so with usual addition and multiplication. With usual addition and multiplication. Because we know with usual addition and scalar multiplication. Scalar multiplication is a real vectors, usual multiplication. Is it a, so now tell me R over Q, I'm asking. R over Q is a vector space with respect to usual addition and scalar multiplication?
Yes.
Yes. Yeah, it's a vector space. So here R is a elements of R. R is a vector space, Q is a field. Okay, it's a vector space. Another interesting example. V equal to R, F equal to R. X
Yes.
X plus X plus Y equal to X cube plus Y cube whole power 1 by 3, where for all X, Y belongs to R, and alpha dot y, X equal to cubic root of alpha into X, for all alpha belongs to R, X belongs to R. So is it a vector space? You have to verify this one. Okay, I will stop. I think too much. If I take, it's not a good idea to continue long time. Whether it is interesting or not, we'll lose the interest after some time. ఇప్పుడు ఈ సిస్టమ్ ఉంది కదా, సో
Yes, sir.
ఇది ఇప్పుడు ఇవి మల్టిప్లై చేసి ఈక్వల్ చేసి ఇదే వస్తుంది, మీకు ఈ సిస్టమే వస్తుంది. చూస్తానికి అలా రివర్స్ అనిపిస్తుంది కానీ ఇట్స్ నాట్ రివర్స్. చూడండి ఇప్పుడు ఇక్కడ A11 X1 ఫస్ట్ కోఆర్డినేట్ తీసుకున్నాం అనుకోండి, ఇక్కడ ఏమొస్తుంది A11 X1, ఇక్కడ ఫస్ట్ కోఆర్డినేట్ ఏమొస్తుంది A12 X2, ఇక్కడ ఫస్ట్ కోఆర్డినేట్ ఏమొస్తుంది A13 X3 కదా.
ఓకే.
సో
అంటే ఇప్పుడు అంటే ఎక్స్ ఏ చేస్తే అదే కదా, ఎగ్జాక్ట్ గా అదే కంపారిజన్ అవుతుంది అనేసి
వస్తుంది సేమ్ వస్తుంది. కాకపోతే మేబీ ఫర్ కన్ఫ్యూజ్ అవుతారంటే మీరు ఎక్స్ ని ఇక్కడ కూడా రాసుకోవచ్చు, X1 ని X1 ఇక్కడ, ఇది X2 ఇక్కడ, X3 ఇక్కడ తీసేసి ఇక్కడ రాయొచ్చు.
Okay, sir.
Okay.
Next.
Sir, small doubt, sir.
Yeah.
GL of n, R అని చెప్పారు సార్, ఇన్వర్టిబుల్ మ్యాట్రిసెస్. అదొక్కసారి ఎక్స్ప్లెయిన్ చేయండి.
గ్రూప్ థియరీలో వస్తుంది సార్, అదే గ్రూప్ థియరీలో వస్తుంది సార్, డీటెయిల్ గా అక్కడ
డీటెయిల్ గా చెప్తారు.
ఇంకా మనకు గ్రూప్ థియరీలో ఇక్కడ ఇవన్నీ ప్రాపర్టీస్ గ్రూప్ అవుతుందా, నార్మల్ సబ్ గ్రూప్ అవుతుందా అక్కడ ప్రూఫ్ చేస్తాం. ఓకేనా సార్? ఉపేందర్ సార్, మన ఎవరు వేణుగోపాల్ రెడ్డి.
ఓకే సార్.
నెక్స్ట్
So field second condition, how to read that one, sir? Field second condition.
సెకండ్ డెఫినేషన్ లోనా ఇదా?
Yes, sir. F such that you have written
No, it's
zeros.
not like that. It is minus notation ని ఇలా కూడా రాస్తారు. Maybe I should have written F.
సార్ పక్కకు రాయండి సార్, చాలా వరకు మా అక్కడ కూడా రియల్ అనాలిసిస్ లో కూడా అట్నే రాస్తాడు సార్.
F star equal to F minus singleton set.
Yeah.
Okay, sir.
ఇది నోటేషన్ అండి, ఇది ఇట్లా స్లాష్ ఫార్వర్డ్ స్లాష్ పెడితే అది మైనస్
Written like that. Okay.
F మైనస్ అన్నమాట. ఓకే సార్, థ్యాంక్ యూ సార్. ఇంకా ఎవరైనా ఇంటరాక్ట్ కావాలనుకుంటే.
గుడ్ ఈవినింగ్ సార్.
yes.
ఇప్పుడు ప్రాపర్టీస్ చెప్పారు, వెక్టర్ స్పేస్ వెక్టర్ స్పేస్ అని ప్రూవ్ చేయడానికి
అవునవును.
ఇప్పుడు ప్రతి ప్రాపర్టీ కంపల్సరీ 10 ప్రాపర్టీస్ వెరిఫై చేయాలి, ప్రాపర్టీస్ వెరిఫై చేయాలి.
ప్రతి ప్రాపర్టీ వెరిఫై చేయాలి. ఒకవేళ అది వెక్టర్ స్పేస్ అని చూపించాలంటే అన్ని వెరిఫై చేయాలి, కాదని చూపించాలంటే ఏదైనా ఒకటి సాటిస్ఫై కావట్లేదని చూపిస్తే సరిపోతుంది. సో ఇక్కడ ఇది అంటే ఇవి యూజువల్ వెరిఫికేషన్ ఉంది, మనం ప్రాక్టీస్ చేస్తుంటే ఈజీగా గుర్తుపట్టచ్చు. ఫర్ ఎగ్జాంపుల్ నేను ఇక్కడ ఇది ఒకటి నాన్ వెక్టర్ స్పేస్ ఇచ్చాను కదా, ఒకటి ఏది ఇక్కడ ఇది ఉంది కదా, ఇది ఇక్కడ నేనేం చెప్తున్నాను, 1 into x, y is not equal to x, y అలా అవుతుంది కదా. సెకండ్ ప్రాపర్టీ స్కేలర్ మల్టిప్లికేషన్ వి హావ్ ప్రూవ్డ్ ఆల్రెడీ.
ఓకే సార్.
సో ఒక ప్రాపర్టీ సాటిస్ఫై కావట్లేదు కాబట్టి ఇట్స్ నాట్ ఎ వెక్టర్ స్పేస్. ఇక్కడ ఇది చూసారు కదా, 1 into x, y is x, 0 which is not equal to x, y కదా.
Yes, sir.
సో ఒక ప్రాపర్టీ సాటిస్ఫై కాకపోయినా ఇట్ ఇస్ నాట్ ఎ వెక్టర్ స్పేస్. వి విల్ సీ సమ్ మోర్ ప్రాపర్టీస్. అది కూడా వెక్టర్ స్పేస్ లో సమ్ మోర్ కాన్సిక్వెన్స్ ప్రాపర్టీస్ చూస్తాము. ఆ తర్వాత దాన్ని బట్టి కూడా కొన్ని ఈజీగా చెప్పవచ్చు.
Yes. Okay, sir. Okay. ఇంకెవరైనా? Yeah.
సార్ స్కేలార్ మల్టిప్లికేషన్ లో ఆల్ఫా సర్కిల్ x, y అన్నారు.
అవును.
ఆల్ఫా డాట్ ఆల్ఫా x, 0 ఎలా వచ్చిందో అర్థం కాదు.
ఇది నేను డిఫైన్ చేస్తున్నాను. మనం ఇది అలానే డిఫైన్ చేయబడింది.
ఓకే ఓకే.
ఇది డెఫినేషన్ అన్నమాట. వీఆర్ గివింగ్ స్కేలార్ మల్టిప్లికేషన్ like this only. Now I am asking whether V is a vector space with respect to this scalar multiplication.
Okay, sir.
So it's given అన్నమాట, ఇచ్చినది అన్నమాట. అది మనకి ఇచ్చింది, మనం డిఫైన్
అంటే y వాల్యూ 0 ఉంది అక్కడ.
0 వచ్చేసింది. సో మనం ఇలా ఇస్తే ఇది వెక్టర్ స్పేస్ అవుతుందా కాదా అనేది క్వశ్చన్.
ఓకే. థాంక్యూ.
yes. Okay.
Yeah, sir. Thank you, sir. Thank you very much, sir. Now I request Shiv Prasad garu to say vote of thanks.
Yeah, good evening to one and all. Dr. Pradeep sir, he is completed BSc in SV Degree College, Suryapeta, MSc from IIT Madras, PhD from IISc Bangalore under supervision of Professor S. Tangavelu sir. Now he is working as assistant professor, BITS Filani, Goa Institution. I am very happy to say that sir is giving today very wonderful and elaborate lecture on basic fundamentals of linear algebra, as like that group, abelian group, field, vector space with different examples. I am very, very happy, sir. I am a lecturer from Gurukulam. Thank you, sir. Thank you for your different way of thinking. Your teaching is very different way of thinking, sir. Your writing is very nice. Thank you so much, sir. And also we are coming from Telugu medium background. I am very happy because he is from our Telangana Suryapeta person, Professor Garu. Thank you so much, sir. Dr. Naggay sir, please take to this, sir.
Okay. Thank you, Shiv Prasad sir, for giving me.
1 minute, sir. One more comment.
Sir.
ఏంటంటే ఇక్కడ బిట్స్ ఫిలానీలో కూడా పిహెచ్డి ఉంది.
సార్
గోవా క్యాంపస్ పిహెచ్డి ఉంది. ఇక్కడ స్పెషల్ ఎంట్రన్స్ ఉంటుంది. JRF
సూర్యాపేట రత్నం కాలేజ్ సార్.
ఎక్కడ?